All right, so here's a more circle example. It's pretty involved. So we have this point in a structural member, and it is subjected to plane stress. So what they're telling us there is, like usual, we can assume that all the stresses coming out of the page and into the page are 0. The normal and shear stresses acting on horizontal and vertical planes at the point are shown. So the reason why Mohr circle, one of the reasons, there's a lot of reasons why Mohr circle is hard, is because we're looking at these little points and it's hard to contextualize what we're looking at. So this is just a point that's maybe on a pipe that has some torsion and some bending and some axial stresses on it and some pressure stresses, all kinds of stresses. And in this one orientation that we're given, these are the stresses it has. With Mohr circle, we can look at all the other combinations of normal and shear stresses. So that's what we're going to do. Because part A is to draw Mohr circle for the state of stress. We're good at that. Then we're going to determine the principal stresses and the maximum in-plane shear stress acting at that point, at the point, so at this point that we're looking at, and we're good at that. And then we have to draw those stresses on an appropriate sketch. We can do that too. And then we're going to determine the normal and shear stresses on the indicated plane and show these stresses on a sketch. So that's a little bit more annoying than what we've done so far, but we can do it. And lastly, we'll do this last thing, is determine the absolute maximum shear stress at the point, because this is one of the easy ones. Okay, so to draw Mohr's circle. So it's good to calculate the center of the circle. And we have an equation of that based on the fact that we have this equation that we developed so that we can make this into a circle. So the center of the circle is the stress acting in the x direction. So we better label this, call this x, and this y, plus the stress acting in the y direction, all over 2. Now let's say you had y and z, that'd be okay. As long as we're in plane stress, it can be any combination of x, y, and z, but there can only be 2 of them. Okay, so here, sigma x is this one, and it's in compression, so we need to make sure we put it negative. So this is negative 3.8 KSI, and then sigma y is up here, and it's in tension, so it's positive 9.4 KSI. Plus 9.4 KSI, all divided by 2. So the center of the circle is at 2.8 KSI. And then we're going to do 2 points. Not just 1 point, 2 points that are going to be 90 degrees apart in real life and 180 degrees apart on Mohr's circle. So our points are going to be the right face. So that's this face right here. So the normal and shear acting on that right face. So I already said that the normal is negative 3.0. Yeah, and this is also what we're calling the x face, the x direction. So we have negative 3.8, and then shear is going to be, if we look at this arrow, it would twist to this counterclockwise. So if we look at our little arrows here, positive goes clockwise, negative goes counterclockwise. So this is negative for us. So this would be negative 5.7. Then let's also look at the top face. So that's in the y direction. So that's 90 degrees away from the x face, so it'll be 180 degrees away on Mohr's circle. So the normal stress is 9.4. And the shear stress is 5.7, and it'll go clockwise. Since they are 90 degrees apart, they have to be opposite in sign. So that one's going to plot above the normal stress axis. So it'll be positive 5.7. So now we can draw these things. So I'm going to plot my center. The center is always on the normal stress axis, always on this axis. So it's going to be 2.8 right here. It's my center. 2.8. Okay, then I need to plot the x face, which is negative 3.8 in the normal stress direction. So I'm going to go 1, 2, 3, 3.8. And then I'm going to go down negative 5.7. 1, 2, 3, 4, 5.7. So right about here. All right, then this is my x face. I'll label it in a minute. Then my y face is 9.4. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9.4. And then I'm going to go up 5.7. 1, 2, 3, 4, 5.7. All right, so those are my 2 points. Now, with the help of my iPad, I can draw an oval and turn it into a circle that pretty much goes through those 2 points. Okay, so this point and this point, let's label them so it's real obvious what's going on here. This is my x face, or the right face, and it is 3.8 and 5.7. And this is the top face, or the y direction, and it is 9.4 and 5.7. And we can connect those with this line. They have to be 180 degrees apart, and they basically go through the center. Okay, so we have a Mohr circle. Part A is done. Now we need to determine the principal stresses and the max in-plane shear. Okay, so we know where the principal stresses are. This is our sigma max. Shear stress is 0. This is our second principal stress, sigma min. Shear stress is 0. But we actually have to calculate what those values are. So to do that, and we're also supposed to calculate the max in-plane shear stress. We know how to do that. Really easy, because that's radius. So let's do that first. So look at this. I left all my notes. Principal stresses and max in-plane shear stress. So first we'll calculate the radius, because that's the max shear stress. So that equation, sigma x minus sigma y, all over 2 squared plus shear stress on the xy plane squared, and the square root of all that. So we plug those numbers in. We have negative 3.8, don't forget the negative, minus 9.4, all divided by 2 squared plus 5.7 squared square root of all of that. So our radius equals 8.72 KSI, and that also equals our shear max in plane. So we have another answer done. But let's plot that. Let's show it. So that happens directly below and above the center of the circle. So I'm not going to calculate what the normal stress is, but right here we have 8.72 KSI. And we're going to mark it down here too. .72 equals tau max. Okay, so now we have to calculate what we actually have. This could also be sigma P1 and sigma P2. So we actually have to calculate values for that. But we figured out how to do that because this distance is the center of the circle, and this distance is the radius. So to calculate sigma P1, it's going to be the center plus r, and calculate sigma P2, it's going to be the radius, the center of the circle, minus the radius. Alright, but we're going to get rid of all that stuff, because otherwise these get too messy. Okay, so now we have that sigma P1, principal stress, equals center of the circle plus the radius, 2.8 KSI plus 8.72 KSI. So that is 11.52 KSI. Let's label it. This is 11.52 KSI. You could do a quick check. This number is bigger than this number. That's good. It better be. If it's not, better check again. Okay. Sigma P2 equals the center of the circle minus the radius. So that's 2.8 minus 8.72. So both KSI. So now we get negative 5.92 KSI. So it better be negative. It is. It's over here. So this is 5.92. And that checks out because this is 3.8. And that seems about right. So all that's good. All right. So now we determined the maximum in-plane shear stress and the principal stresses. Now we need to show them on an appropriate sketch, which means we need the angle, because the sketch can't be appropriate if it's not at the right angle, the correct angle. So that means that we have to calculate 2 theta on Mohr's circle. So I'm going to not make a silly mistake. I'm going to focus on my right face. And I'm going to move my right face to sigma P2, or sigma minimum. So I'm going to calculate this 2 theta. And I know that this is 5.7. And then I need to calculate this dimension that we could call A, because I also know that this dimension is the radius, which is, so then I don't even need to know A. That's right, we're not calculating A, but that's what happens here. So the radius is 8.72. I don't need to write the dimensions. 8.72, so then I don't need A. This makes it even easier. We want to make things as easy as possible. So now we can do, so with that we can do, this is the opposite and this is the hypotenuse, so we can do the sine of 2 theta equals the opposite over the hypotenuse. So we have, back down here, that's one thing, is going back and forth to your Mohr circle gets annoying, but that's the way it goes. So we have the sine of 2 theta equals, opposite was 5.7, the radius, or the hypotenuse, was 8.72. So that means that 2 theta equals 40.82 degrees. That's on Mohr's circle. That means in real life, we need sigma equals 40.82 divided by 2. So we're going to rotate 20.41 degrees in real life, and we have to pay attention to which way we're rotating. We're rotating from this point to this point. It's clockwise. All right, so now we can draw this. So I start by drawing my original right face, which was just a vertical line. My new right face rotated 20.41 degrees clockwise, making it a straight line over here. And it's very important to label this angle. Now, I'm gonna choke. I'm choking because I hate drawing squares at an angle so much. Okay, but I'll try. Something about like that. We'll go for it. Just going for it. And then we connect them. It's a little off. Bit more of a diamond. It'll be okay. This is the principal plane, so there are no shear stresses on it. It's very important. So, remember, this was my original right face. So now I need to plot this on my new right face. So that's going to be in compression, 5.92. So go back here. My original right face was here. My new right face is here. So I have compression. This is 5.92. And this is compression. Well, we don't have to label that side. It's the same. Okay. Then the top face. So if I rotated, this is also 2 theta. So that one, the Y face went, oh, I didn't put a 2 theta. The top face moved to this, the sigma P1 or sigma max. So that's 11.52. So, and that's in tension. So then here, I draw this. 11.52. These are KSI. Okay, we're making progress. So now we got through B. Okay, now this annoying part. So we need to determine the normal and shear stress on this plane. So this is kind of like what we were talking about. You have something coming. We have this new axis system. It's going to be something like that. That's what we're looking for. So we got to get to it. It's not going away. All right. So part C. Normal stress and shear stress on the new plane. So we could call it, like we did back in chapter 1, this is our normal to the cut and tangent to the cut. What's important here is it's nice to know the angle relative to x, because we know our x and y faces. So that helps. Cutting it apart like this, I think, is worth your time. I'm glad I did it. All right, so now I have this angle theta, I have this angle alpha. I need to figure out what this angle alpha is first, so that then I can figure out what theta is. It's all very convoluted because they told me that I have a 5 and a 4. So turns out I do things convolutedly sometimes. But so if I have tangent of alpha equals 5/4. So that means that alpha equals 51.34 degrees. Now theta is going to be 90 minus alpha. So because that would make this angle here alpha, and that would make, and then we have this is a 90-degree angle. So theta equals 90 minus alpha, which equals 38.66 degrees. Now we have to pay attention to what direction it's going. It's going, there's Ada barking. She likes to protect my house. It's going to go counterclockwise. Okay, so we got that. So we're going to go 38.66 degrees counterclockwise. But that's in real life. What are we going to do on Mohr circle? I'm going to do twice that. So 2 theta then is going to be 77.32 degrees counterclockwise. And that's on Mohr circle. Because we don't know what those stresses are unless we use our Mohr circle. So I did my trick where I copied my Mohr circle down here. So now what we're doing is we have our x face, and it's here at 3.8, and now we need to move over which direction? Counterclockwise. Looks like I went clockwise. Oh no, I didn't. I get confused on clockwise and counterclockwise sometimes. Okay, so we have to move over 77. So this is hard. So you kind of have to guess what a 77-degree angle will look like. So we're here, right? So this is our line. And now we need a 77-degree angle coming this way. So something like that. And it has to go all the way across. So let's just see what we come up with. Maybe something like that. The biggest thing to know is that you know what 2 theta is. Is that right? Our original 2 theta. That's this. So we know what this is. So we knew how to get from our right face to our sigma P1. Is that what we called that? P1 or P2? Sometimes I get P2, sigma min. So we knew how to get there. And now we know that this angle is this 77.32 degrees. So then this is our new sigma in the normal direction, if we're calling this our normal, and then our tangent component is here. So this is our new sigma normal. And then tau, our shear stress, in the normal and tangent plane. And over here, we have our new, this will be sigma tangent, and our shear stress in the normal and tangent direction. Okay, so we can do this. So now we just have to calculate what these are. So to do that, we can find out, not that color. What color should we use? We'll use pink. We can find out what this angle is. We're going to call this angle beta. So we can say that beta equals 180, because we're going to start with using this whole line, because we know this line is 180, we know 2 theta, we know this is 77.32, so all we don't know is beta. So that's what we're doing. We know it's 180, subtract 40.82, subtract 77.32, and we get beta. All right, so beta equals 180 minus 40.82 minus 77.32, and we get beta equals 61.86 degrees. Okay, then we know this is R, so this is 8.72, and we know beta, so we can say, I did this a weird way. Oh no, I didn't, it's good. Because to calculate what this is, we need to start, we're not starting at 0. The center of the circle is not at 0. So we have to say, we have to go from 0 to the center of the circle, and then add in this distance, which will be the cosine of beta times 8.72. So I'll write that out. So sigma n equals center of the circle plus the radius times the cosine of beta. So that equals 2.8, plus our radius is 8.72, cosine of 61.87 or 86 degrees, then our new sigma normal equals 6.91 KSI. And it is in tension. It's positive. All right, so no part of this is 6.91. Now we need to find out what the new shear stress is. So that's just going to be tau nt equals, we don't need to worry about the radius now because we only need this distance. So it's just, we need to worry about the radius but not the center of the circle. So it's the radius times the sine of beta. So this is 8.72 times the sine of 61.86 degrees. So we get tau in the normal, the shear stress in the normal tangent plane equals 7.69 KSI. Look at us go. Okay. All right. So what else do we have to do? Probably have to find those other stresses. Or is that all they told us to do? That's all they did. Determine the normal and shear stresses on the indicated plane. That's all we have to do. Oh, then we can show them on. Okay, well, we're going to cheat a little bit. We're not going to draw the whole stress block like we normally do. We're just going to do this. So, looks like what I did is I took this. Well, I could do this the proper way. We're going to do this the proper way. So, if we draw then we have to find this one too, but that's okay because this is also beta. So I'm just gonna have to do a little math in the background. So then we would have normal stress sigma t equals, we need this distance, so we need to calculate all of this and then subtract c. So we would have sigma t equals, we could do like we did before, c minus r cosine of beta. So this equals 2.8 minus 8.72 cosine of 61.86 degrees. Sigma t equals, let me calculate this really fast, equals 2.8 minus 8.72 times cosine d of 61.86. Okay, so we're at negative 1.31 KSI. I buy that, looking at our imperfectly drawn picture here. And the shear stress will be the same. So now this is our original right face. We're going to rotate half of 2 theta. So we have to calculate theta in real life. Oh, we already did. That's up here. So we're going to rotate 38.66 degrees counterclockwise. So our original right face was vertical. Our new face goes counterclockwise by, how many degrees did I say? 38.66. All right, I didn't leave myself very much room. I'm kind of squishing this in here. All right, oh, and then I need this. Okay, so this would be something, is that right, or did it go down like this? It goes down like this, oh boy. Okay. And it's kind of a rectangle, but you get the point. And this angle is 38.66. Gotta remember to label that. Okay, and then on our new right face, which is here, oh, I forgot to label what this is. This is 6.91 and 7.69. This one up here, negative 1.31 and 7.69. Okay, we're almost done. It's a good thing I didn't do this in class. It's taken all day. All right, so now we just draw these. So this is not a principal stress plane, so we're going to have normal stress and shear stress. So we're going to have, this is in tension, 6.91. This is my new right face. New right face. And then this one's going to be in tension. Same value, 6.91. On that right face, I have a shear stress that is going to rotate things counterclockwise. So that means it's going to go that way. So it's going to go up. And that value is 7.69. Okay, so max shear stress. Hold on here. I'm going to make sure that makes sense. Yep, that makes sense. Okay. So then that means this one's going to go this way. This one's going to go this way. And this one's going to go this way. And they're all 7.69. But now I need to label the new y face, or the tangent, and that's in compression. And that's 1.31. KSI, right? KSI. 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 And that's 1.31. All right, there you have it. So get ready. That's your last homework problem.